Yeah, so that's great. And please take it away. So share your screen.
All right. Future direction slide a second. Can you see the slides? Can everyone see the slides?
Yes, we see some.
Oh, okay, all right. Oh,
yes.
Yeah. Thank you. So I am Stav, as Mark already told you, and I would like to first thank the organizers for giving me this chance to present this work that I did over this year. And so let me just begin. So what I will be discussing is these relativistic effects in optical quantum interference experiments. So kind of the main theme of the let me just adjust my screen for a second. Just a second. Yep. Yeah. So the main kind of theme or a very short summary of whatever I'm going to say is the following: that we have these relativistic effects, which are both special relativistic and general relativistic effects, which come into play if you have very sensitive interference experiments, quantum interference experiments. So what these effects in general do is introduce differences in space-time paths. So by differences in space-time paths, what I mean is that if you had, for example, interferometers where the photons were traveling along different space paths, that their trajectories were themselves different, you would have different effects on the two paths, or on the paths that the photons take. So, for example, the gravity of any source would affect them differently. There could be time dilation effects because of the motion of the interferometer, which would affect these two paths differently. Or you could have situations where actually the space path is exactly the same. For example, the diagram that I kind of show on the left, this is a kind of Sagnac interferometer or a ring interferometer, where the photons just travel on the same path but in opposite directions. So this would actually mean that the photons are traveling along the same space paths, but if you were to move this interferometer in a certain way, the space-time path would change. So time dilation effects also play an important role. So so the space-time path differences can be caused either by actual space path differences or differences caused by general relativistic or special relativistic effects, which affect the proper time of the measured time of the observer. So on the right, what I show is the space-time diagram of the two counter-propagating photons in this interferometer. So even though they travel along the same path, after a certain time they develop a time lag, so as to say that they reach back to the same point at different times. And this is what I mean by this space-time path difference. So what will happen because of this time delay or the space-time difference is that the photon beams which were in phase, for example, to start with, would not remain in phase after a certain propagation time. So these phase differences will then ultimately lead to changes in the interference pattern. So the interference pattern, for example, the visibility could change. You could have different coincidence counts and so on, as I will talk in detail. But the big picture is that relativistic effects lead to differences in space-time paths. Space-time paths being different lead to different phases for the propagating beams, and that will affect the interference pattern. So that is going to be the kind of core of my argument all through. So let me just move to the next slide. Yeah. So this is a work that, as Mark also told you, I did with Anthony Brady, who is also a graduate student here at LSU. And this is on archive currently. It's under review in a journal. So let me move on. So let me first begin by kind of introducing some of the effects that I will be. So in this work, we try try to measure the effects of. And so the first relativistic effect is kind of a kinematical effect in the sense that it doesn't depend on the presence of any gravitational source. It's just because of the motion of the interferometer. So consider a kind of fiber optic ring, which say is initially stationary, and you send two beams in opposite direction, two photons in opposite direction. They will have equal transit times, and then when they come back to their original point, their starting point, if you were to do interference measurements on them, you will see that there is no phase difference, because if everything else remains the same, because they essentially travel along the same path. But now if you started rotating this interferometer, classically you would still believe that the photons will reach at the initial point at the same time, because the velocities of rotation gets added to one of the photon path and gets subtracted from one of the photon path, but then one of them has to travel a larger distance and the other one has to travel a smaller distance. Or if you look at it from the frame of reference of the photon itself, it's simply they travel along the same paths and nothing changes. So classically speaking, even if you started rotating this, and by classically, sorry, I mean Newtonianly, in Newtonian mechanics, I don't mean classical in the quantum classical sense, quantum versus classical sense. I mean in the Newtonian versus the relativistic sense. So if you were to consider just Newtonian effects, they would still have no time lag. But if you look at it from the perspective of special relativity, you would say that, all right, the length of the interferometer up to first order and velocity will still remain the same for both the propagating beams, but one of them will have a kind of positive time dilation for in some sense, because the velocity gets added in the Lorentz transform. The other one will have like a negative time dilation, and so after they have propagated through this ring, you will see a difference in the arrival times, and that translated into the phase difference will be proportional to the angular frequency of this rotation, because this time difference is obviously proportional to the velocity and also the area of the interferometer. So this is a typical Sagnac effect that you see in interferometers. It's proportional to the angular frequency, and it's also proportional to the area of the interferometer. And these are some things which are actually important, because you can design very fast rotating interferometers or very large interferometers if you want to see this effect. So Michelson, Gale, and Pearson way back in 1925 actually used a Sagnac kind of interferometer to measure the angular frequency of the Earth, the angular velocity of the Earth. And this is in line of all the experiments that were done in those days to trying to refute general relativity, but ultimately, yeah, we know what happened. So let me move on quickly. So now there are other gravitational effects. So the so-called dynamical effects, in the sense that they require a source of gravity. So for example, there was some source of gravity sitting at the center of this ring. By ring, I mean some rotating object, some object going around this central mass, and the object itself had a certain angular momentum. So if the angular momentum initially pointed towards some distant star, after the object has gone around this central body, gravitating body, if the space was flat, as per Newtonian gravity, you would obviously feel that the angular momentum vector would still remain pointing along the star. But if, as on the right hand side, you would see that if this central mass kind of warps the space-time around it, it develops a kind of bending in the space-time around it. The angular momentum vector, once it, and this is very much related to parallel transport, once it comes back, it changes the direction of the angular momentum slightly. So it no longer is pointing towards that fixed distance star, relatively fixed distance star. So this effect is called the geodetic effect, and this happens for any rotating observer around any massive object. So The next effect is a kind of counterpart, but in the sense that it also rotates the angular momentum, but it's a slightly different effect. So, for example, consider now a rotating mass in the center. So, for example, in this figure, the mass at the center was just stationary. It's just static space-time. Nothing is changing. But in the second case, consider a space-time where the central mass is also rotating. For example, the sun or the earth or other astronomical objects. And the analogy to this in a coarse way is to consider a spinning ball inside some viscous liquid, honey. Once it starts rotating, it drags the viscous liquid with it. The closer the liquid is, the faster it is dragged. The farther the liquid is, the slower it gets dragged, or the lesser amount it gets dragged by. So if you had then an object going around a rotating mass, a similar general relativistic effects also takes place, and the frame itself gets dragged. So the object itself will kind of encounter this dragging. So once it has come to this point, its angular momentum would have dragged all kind of position vectors and so on. Angular momentum vector and or quantities like this would get shifted slightly. So the tilt would change. So if you had these rotating masses, you could still you could observe these kind of effects on angular momentum. These effects, both these effects, the gravity probe B tried to measure these effects. With the geodetic effect, because it's a larger effect, they were able to do it within 1% of accuracy. But for the frame dragging effect, because it's a much smaller effect, as you can see, it just 39 milliarc seconds a year, whereas the geodetic effect is just like still measurable in degrees, although it's a thousandth of a degree. But it can be measured, whereas the frame dragging effect, that measurement just faded away in the noise. So people could not verify that, but the geodetic effect was definitely verified. So this was about the general relativistic effects that we tried to kind of quantify for quantum interference experiments. And now let me just briefly kind of give an introduction to the actual experiment that we will be doing. So that's based on the which we'll be studying, not doing, which is based on the Hong-Ou-Mandel interference. So the Hong-Ou-Mandel interference is kind of the most basic example where photon bunching takes place, or the bosonic properties of photons come into play. So if you consider a simple beam splitter and you send in two input photon beams into it, or wave packets into it, and then you detect them on the other side. So you have two input ports and two output ports. There are four things that can happen. So either both of them can get reflected, one gets reflected, the other gets transmitted, and vice versa, and both of them can get transmitted. So if these photons were completely distinguishable, as classically we consider all particles to be distinguishable, or kind of the Boltzmann distribution, you would not have the amplitudes affect each other in any way. They all add up, the probabilities all add up. So there is a 50% probability that the both the photon beams will get, like one of them will get reflected and the other will get transmitted. And there is a half chance that both of them will get reflected and both of them will get transmitted. So the coincidence counts on the other side, that which occur when you have one reflection and one transmission, will be 50% of the times. So 50% of the times you see a coincidence. Whereas if you went to a quantum mechanical description, these are all identical photons. So this reflection, because it introduces a pi phase difference, these amplitudes where one is reflected and one is transmitted just get cancelled. So the amplitudes themselves get cancelled, and then the probability of the coincidence count just goes to zero if the particles are completely distinguishable. And now there can be a kind of in between situation where you have some amount of distinguishability that comes in because, say, differences in polarization or phases and so on. And then what you will see is that this arrival time difference, as you vary this arrival time difference or the path delay or the phase difference, which all are the same things, you will see a dip in the coincidence counts, which goes to 0 at some time difference, which actually, if you set everything else the same, then if delta t is exactly 0, then the dip is at its lowest, which is also 0. So there will be no coincidence counts. So why this experiment is a good kind of measure for the quantum classical regime is that if you were to describe these photon beams as electromagnetic waves or classical electromagnetic waves, you could still kind of describe you could still get a dip in the number of coincidences with added distinguishability, but that dip can never go to 0. That dip can only go to half of this this total number of coincidences. Whereas quantum mechanically, we know that this dip can completely go to 0 because particles can be completely indistinguishable. So you have this very good kind of barrier between the quantum and the classical descriptions. So which one is sufficient? So if you have the visibility of this dip greater than half, then you must have a quantum description for the fields. So now let me just quickly move on to what the actual setup that we kind of try to measure these effects for, find out what these effects are for. So this is again kind of a ring interferometer. You have two photon sources. You send in counter-propagating photons. They travel along these two paths, and when they come back, they are passed through a beam splitter, and that's why this HOM effect comes into play. And you measure the coincidence counts at the end. And this setup is present on the surface of the Earth, and the Earth is rotating. So you have the Lenz-Thirring effect, you have the geodetic effect, you also have the Sagnac effect. So you have all these effects that come into play. And you try to see what these effects do to the coincidence counts. All right, so let me move on. So it's a bit late for motivating you about the talk, but okay, let me do it anyways. So why this is important? As I said, this will be a quantum interferometry experiment, a quantum interference experiment in curved space-time, because you are talking about a gravitating body at the center, like close to the setup. It's also rotating. So you are necessarily dealing with a quantum interference experiment in curved space-time. So this gives you a good setup where you can look at the interaction between general relativity and quantum theories, which we do not understand very well, because quantum field theory in curved space-time is still it's a kind of set of hypotheses and based on that you make certain predictions, but nobody knows if it's exactly right. So it's a good testing ground for that. And as I said, this HOM interference experiment with this kind of a Sagnac topology offers a very good setup for this, because to see this interaction, because a good barrier between or a distinguishing feature between classical versus quantum effects descriptions exists, which is the visibility criteria. If the visibility is less than a half, then greater than a half, then you are sure that you must describe these this interference experiment with quantum fields. And also, because this frame dragging effect that we see, both the geodetic and the Lenz-Thirring effects, they are purely general relativistic effects. They cannot happen in flat space-time. The Sagnac effect, on the other hand, is just a kinematical effect. So you can see that even if space-time was flat, but the frame dragging effects, the geodetic effect and the Lenz-Thirring effect, both of them together, those are effects which cannot be seen if the space-time is not curved. You will have to have a general relativistic description to see these effects. So if you want to be sure that you are doing an experiment where both quantum mechanics, where both quantum theory and general relativity are applicable, this is a good kind of a setup. So then applications from the practical point of view, multi-photon experiments, as they get more and more sensitive, you will need to include these GRFX. Although not completely related to what we have done, is the LIGO experiment, for example, where if it is, as it has become very sensitive, it's actually measuring a general relativistic effect, so which is gravitational waves. Then from the practical point of view, as we go on to set up these large scale quantum protocols, either communication or cryptography, with satellites and ground stations sending entangled photons to them and so on and so forth, you will need general relativistic effects definitely to come into the picture. For example, even in the classical realm, if you have the GPS, general relativistic effects are extremely important. So with these quantum effects coming in, sorry, is there a problem with the audio?
Your audio is getting lower. Yeah.
Can you hear me now better?
It's better, yeah.
Oh, sorry.
It
Maybe
seems like that little thing is bouncing around, and so when it bounces far away from your mouth, it gets very
so maybe
quiet.
I should not move my head too much. I'll just hold it. I'll just hold it.
As the talk progressed, I think you were moving more and more or something.
Yeah. Sorry. I'll just. So could you hear me sufficiently to kind of get what I was speaking, or should I go back and speak about some things again, or should I just go on?
Just proceed.
Okay. Sorry. Yeah. So I'll just hold it this way. As I was saying, from the practical point of view, there is this quantum communications protocols, which will be, it will be important to see these effects there. And at the most kind of, at the face of it at least, because this HOM interferometer is so important for all quantum optical technology, even optical quantum computers, this is like the basic effect that happens everywhere. It's definitely important to encode these general relativistic effects into it, because if you have higher and higher sensitivity, you will see these effects come into play. So let me move on. Oops, sorry. And discuss the main methods that were used. So this is basically quantum optics in curved space-time. So we start with a classical Klein-Gordon equation for a scalar field, because we don't consider how the polarization is affected. So it's not a vector field, it's just a scalar field. And we do the standard mode expansion for the field, where phi k is the field for a particular mode, wave number mode. Alpha is the amplitude of that mode, and sk is just the iconal or phase. The phase.
Stav?
Yep.
Sorry. Can you put your mic just in front of your mouth, because otherwise the volume.
Yeah. Is it better now?
Yes, it's better, but keep it there, please.
Okay,
yeah.
I will just keep it there. Yeah. So as I was saying, this phi is the scalar field, and the mode expansion is in terms of the wave numbers. Alpha is the amplitude for a particular mode, and sk is the phase associated with that mode. So what we do is then think about this setup as adding a small perturbation to the flat space that we have, the flat metric that we have. So this can be understood in two ways. A, that the gravity of the Earth is weak. It's not a very strong gravitational field. Therefore, this perturbation, and it's also not varying very fast. So you have a weak field and slowly varying gravitational field. So you can do such an perturbative kind of expansion for the metric, which is around the flat space-time. Or you can think about it in the sense that you are not going very far from the world line of the observer. So you are very close so the paths that you are dealing with are very close to where you have your detectors. So if you have the equivalence principle tells you that the space has to be flat locally everywhere. If you go and have very small displacements, then definitely it will remain almost flat. So, and because of the fact that Earth is like a very weak gravitating body, this close is almost a light year. So it's a good approximation in that sense. So as long as we are not building interferometers which are large. So what this small perturbation to the metric eventually does is add a small perturbation to the phase and to the amplitude. And this is what we want to see, that what this small difference in the phase is because of this perturbation in the metric. So what you try to do is first write down the metric in a proper reference frame, which is the reference frame fixed to the observer. And in this case, the observer is just the detector where you are taking the coincidence counts. So you write down that metric, and its components are just in terms of the local accelerations and rotations that you can measure at the detector. So you could have gyroscopes, you could have accelerometers there sitting there and measure these rotations and accelerations, and then write down the metric in terms of those. But then you would also want to relate these metric elements to the angular velocity of the Earth, the acceleration due to gravity at the Earth's surface, which are known. So so
we just
yeah.
you know, the end time. You should probably wrap up.
Yeah. I'll just take maybe 2-3 more, 4 minutes. Yeah. So also let me just quickly.
The other thing is that, sorry, the other thing is that if you hold the mic too close, we're getting a lot of pops.
Oops, sorry. Is this better?
There's some sweet spot, I guess.
Yeah.
Stav, can you try without the microphone? I think your laptop can pick it up better.
I don't know if we should do any big adjustments now because we're essentially we're out of time.
Yeah. Sorry, is this any better?
It's better, yeah.
All right. So let me just quickly move. So so you can now relate these angular velocities and the accelerations to the acceleration due to gravity on the surface of the Earth, the centrifugal acceleration, and the u is the potential at the surface of the Earth. So you find out these things, put them back into this metric, and you can get the by comparing the g mu nu with the flat metric, you can get these h mu nu terms, which will tell you what the perturbation in the metric is. So from there, you can just put them back into your these perturbation equations, and you will get what the difference in the phase is because of all this. So that's the core method. So it's the main point here is just that you need to find the local accelerations and the rotations. So why is this not moving? Yeah. So the result is you can see these path differences. So the first effect is just the Sagnac effect, depends on the latitude, depends on the orientation, the angular velocity of the Earth and the area. And then you see these smaller geodetic effects, geodetic and length ring effects, which also depend on this extra gm by r term, which is smaller by that 1 by c square factor. So it's smaller. And once you have this delta t, you know how it relates to the visibility of the interference pattern of the coincidence counts. So let me quickly show a few graphs, and I don't know why this keeps getting. So this is how the Sagnac shift varies with these different with the orientation of the interferometer and the latitude at which you are measuring. And so if you keep changing the orientation of the interferometer, the shift in the HOM dip will kind of translate to one side, and you will be able to measure the effects on the dip shift if you know what this orientation is and so on. So now and so the only thing that I want to kind of focus on is this kind of order of magnitude estimate. So let me quickly just move to that and end there. So because I'm short of time, as you see. Okay, so the Sagnac shift is around, if you want to measure it in terms of this angular velocity of the Earth, it's 10 to the power minus 15 seconds per kilometer square of area of the interferometer ring. So if you had a kilometer square of area in the interferometer ring, it might sound very huge, but if you have multiple loops, then it's not that much. It's if you had a meter radius interferometer and a 2 kilometer long fiber optic cable, then you get a kilometer. You get 1,000th of a kilometer square. And if you get 1,000th of a kilometer square, the delta T that we can nowadays, it's the state of the art thing, is attosecond delta T that you can measure. And if you can do that, then the area that you need is just 1,000th of a kilometer square. So you can do that. But for the general relativistic terms, it's 9 orders of magnitude smaller. So it's very small. But you will need this large an area. But that, again, with this delta T improving, you can also improve the area certain. So if you had, say, 10 kilometers of length and 100 meter long radius, then you would be able to measure. But then you will need a lot more sensitivity. So, but it's within reach sometime in the near future. So, but the Sagnac can be done now, for example. So, with the current efficiency. So that's all I wanted to say. It's a quick summary. Is that or maybe should I just stop?
Thanks, Stav. I think we should stop.
Yeah,
now.
I'll just
Sorry about that.
Yeah.
So if you have questions, I think it's important that we stay on track and we leave enough time for adequate breaks. So if you have questions for Stav, please write to him in the chat. You can write in the Zoom chat, or you can write an email. I did want to make, so thanks for your talk, Stav.
Thank you.
I did want to make